Yeah.
Oh, I'm going to do it by hand. Oh.
I also got had a Bluetooth module and found some freeware for BlackBerry that'll receive and log it. And then there's like crude mapping software on there, but you can just use it as a portable data logger and then upload it to a PC later.
Well, it's so ridiculous because I mean the GPS units on the market, the receivers in them cost like $70 or $80 but you know, and you buy like a $300 essentially another PDA that only does maps.
Right.
It's just frustrating, and they don't do them well. I mean, if you really want something decent, you're talking like $500, you know.
Right.
Because I want to do something I can actually, you know, I do a lot of hiking and I want something I can actually pinpoint and, you know, and actually interface with pretty easy, and I don't want to buy another gadget.
See, that's why I can never live without my BlackBerry GPS on the...
Yeah, I got the one Pearl that doesn't have a GPS built in.
Oh, really?
Yeah.
Oh, I use it all the time. Like, I road trip to Florida for spring break. I've been so lost with it. I just, no matter how lost you get, you just pull out your phone, go.
Yeah, they're always nice. I'll bring in that one laptop per child on Wednesday if you want to see it.
Yeah.
Do you do any geocaching?
No, I haven't. It sounds like fun, though.
I'm gonna do.
All right, we have no video display today. And it's possible it's actually the projector. I'm not sure. But I should have brought my other laptop in to experiment. But so I'm going to do this on a blackboard. Means you'll miss some cool pictures I had. First of all, on the 20-point homework, excellent job. Everybody who turned it in got essentially got the solution. There were a few technical problems with some of the submissions. There were a few cases where a file had the wrong name, or the files were in a subdirectory, but they weren't in a subdirectory in the upload that you gave me, and so on. So in most cases, I was able to fix those pretty easily. One submission turned in a wire that actually went the wrong direction, and I sent that back. And if you still want to change it to go in the right direction, please do that today. Otherwise, you'll lose some points for that. And there was also one submission that was missing a file. I think the file for going from west to east, and I returned that assignment with a note. So I know you know how to do that, so just turn that in today if you can, and you'll get full credit. The other thing was, I was intending on this homework that you used the set and compile commands into memory. And there was at least one person who actually barehanded set the inputs to 1s and 0s for each of the truth tables and sort of did all of this stuff by hand, which is perfectly fine. It's a good solution, but it's a lot harder than things need to be. So if you don't know how to use the memory commands, or if you didn't do the homework or you have questions about it, please let me know, because like I say, we'll be working above the individual bit level from here on out, but it's good to kind of know what's going on at effectively the machine code level. I was going to show you some demos of it, but I can't do that without the display. Basically, the key to the homework, you needed to do an initialization step that created a first pair of program channel and control channel cells, and then you just use those to configure an extended wire as your standard 3 or 4 step sequence. I think pretty much everybody got that. Some people did a pre-clear, some people didn't. That was fine either way. But if I get this working on Wednesday, I'll show you an example of kind of the different effect of having a pre-clear in there or not. It's an easy way to sort of see what that's all about. Another topic, I'm going to give you a chance to do presentations in here if you want. And you can do presentations for up to 40 points. So a couple of ideas. If you're doing a project and you want to give a talk about it, so this will be like a 20-minute talk or more if you want. If you want to give a talk on it, you can do that. If there's some area that you're interested in related to self-configuration, fault handling, scalability, self-organizing systems, anything like that, and you want to research it and just come up and give a presentation on what you found, that would be great. Up to 40 points, 20-minute talk, easy way to bump up your grades. And that'll be any time before the end of the semester. We'll probably pack them towards the end. And just like projects, if you have ideas and you you want to bounce them around, let me know, shoot me an email or come talk to me. All right, I'm going to change topics here. Let me give you a question. What is a computer? Right? We're engineers, some of us are computer scientists. We work with computers. Computers are in our phones. What's a computer? What's a working definition?
Takes data and a command and executes it. Gives you an output.
Okay, good. Takes data and command, executes it. Gives you an output. What else?
For every input, it gives a predictable output.
Okay.
And
Must
just
run
like
Windows.
machine, little mechanical computers they used to have.
Right. Good. Anything else? Do you know what the first computer was?
What's
Wasn't the mechanical one at the IBM or the company that used
Olive
IBM
machine?
made for the census? Like
That was an early
1880
one.
or something.
Well, are we talking electronic or something more like something Charles Babbage would have made?
Either way.
I'm saying the somebody just said
Abacus?
Yeah. I can't
Abacus,
say the
right?
word.
That's an early computer. First time the word computer was used, it applied to people. A computer was a job. It was a person.
Oh, right.
And their job was to compute. They would crunch numbers, basically, and they were called computers. And when electronic computers and mechanical computers started to be used for the same thing, people always distinguished this is an automated computer or this is a mechanical computer. But computer was actually a human being. Same with the library, like we talk about runtime libraries. The early libraries, those were people also, and they had stacks of programs, paper tapes usually, and when somebody wanted to compile a Fortran program, they would go to the librarian and they would give them this compiler and load it into the machine. All these things were done by people. So yeah, lots of different kinds of computers. I'm going to have to show you these pictures next time because they're just too cool. Very early type of computer was called an analog computer. And an analog computer didn't have a CPU, it didn't have memory, it didn't have flip-flops, it didn't have logic gates, but you could use it to do computation. And there was one in the early 60s, I don't know if you can, what the angle is like on these. This was a really, really early analog computer. I actually had one of these when I was a kid. And it's basically three dials. You can place these in different positions. It had a meter. It had some kind of switch. A few light bulbs and stuff like that. And you could wire this thing in the back to do different functions. For example, you could wire it one way, and if you wanted to multiply two numbers, you would turn this dial until it pointed to the first number, and you turn this dial until it pointed to the second number, and then you would hold down the switch, and this meter would give you a reading, and you would turn this until the meter read 0. And when it read 0, this would be pointing at the product of those two numbers. Okay, really weird way to calculate. And it was, you know, I'm sure my parents paid like $5 for it in the 60s, right? So, powerful way to do computation, but very different from what you sort of think of today. Now, how do you do analog computation?
System fires.
Say again?
Resistor dividers.
Resistor dividers, that's definitely one way to do it. I'm not going to draw this circuit. Do you know what a capacitor is? Does anybody not know? Capacitor is basically two pieces of wire connected to two plates of metal, and those plates don't touch each other. They're very close to each other, but there's no physical contact. So, if you have a capacitor, the symbol looks like this. That's actually what it physically looks like, two pieces of metal, wires going into each one. No connection, okay? If you put some voltage source on here, there's no current flow, because there's no physical connection for the electrons to move. But, in fact, if you apply a voltage that's changing over time, you will get a current flow. If this voltage starts oscillating back and forth, you'll get a current flow proportional to the derivative of the voltage. Okay, this is a useful thing. This little device, two pieces of metal that aren't touching each other, does calculus. Okay, it computes derivatives. You put in any function that you want changing over time, it'll tell you the function that corresponds to its derivative, how it changes with respect to time. And you can read that out as a current. A little piece of metal, and it does calculus. And the fact is, the whole universe does calculus. Okay? We spend a lot of computing power and a lot of research time trying to do things like model the behavior of a wave when it crashes on the beach. And we can't do that. It's too complicated. But a little bit of water and some sand performs these calculations all the time and solves these equations. Okay, in this room right now, there's millions of simultaneous differential equations all being solved in parallel, in real time. Everything you do, every breath you take, every heartbeat, changes the temperature of every molecule in this room. And there's no way we can model that with any of our computers. You can't even do it with a cell matrix. But somehow, the material in this room solves this system of equations and comes up with a solution, and each molecule assumes its correct temperature continuously. And so the whole universe is a computer, in some sense. Now the fact is, most of our computers, the ones that say Intel and AMD, they basically do what you said. They map inputs to outputs. Take a set of inputs, generate a set of outputs. Okay, what forms do the inputs take? What kinds of things do computers ingest to process?
User input from the device or files.
Okay, user input from a device or files. What form would that input be? Binary. Okay, it could be numbers, letters, characters. But in the end, it all boils down to binary. We basically take all this stuff and we treat it as ones and zeros. And so you can think of them as integers or something like that. Basically binary numbers coming in and essentially the same thing coming out. Okay, what about music? You feed music into a computer and you do some signal processing, noise reduction, whatever. And again, I mean, it's basically just a string of ones and zeros. You look at a CD, it's 700 megabytes of ones and zeros. You look in the WAV file, it's the same thing. You can input from various devices, temperature sensors, pressure sensors. And again, those are usually transformed. You take a voltage, you convert it to a digital number, and it goes back into ones and zeros. So these are all your inputs. And you write programs, and you run them on bigger programs called operating systems, and they generate outputs. And so in a sense, all your computer is ever doing is implementing a function, y equals f of x. Okay, which brings us